morning, students. I'm Chaitanya, Assistant Professor in Mathematics, Freshman Engineering Department, Institute of Aeronautical Engineering. And today I'm going to discuss an important concept, QR factorization, in the order of dimensionality reduction. Okay, so let us look into the topic in detail. So, as you know, the subject title is the probabilistic modeling and reasoning. And in this subject, we have already discussed two important concepts. First, we started with the dimensionality reduction. We have discussed what is dimensionality reduction and how it plays a vital role in machine learning. Later, we have entered the mathematical perspective of dimensionality reduction. As a part of that, we started principal component analysis. So, in the last class, we have discussed what is principal component analysis and how it is applied to a data set to reduce its dimensionality. Okay, we have discussed it in a bird's view. Now, today, we are going to discuss one of the important dimensionality reduction method under principal component analysis, that is QR factorization of a matrix or QR decomposition of a matrix. Let us look into the details. So, any matrix A can be factorized into a product of two matrices, namely Q and R, where Q behaves in a certain way called orthogonal matrix and R is an upper triangular matrix. So, under QR decomposition, we will decompose a given matrix A into a product of two matrices Q on R, where Q is an orthogonal matrix. Of course, I am going to explain what do we mean by orthogonality of a matrix. As well, R is the second matrix. R is an upper triangle matrix. Of course, the meaning will be explained in few minutes. And here A is written as Q into R, where Q is orthogonal matrix and R is an upper triangle. This kind of decomposition is called QR decomposition, and it plays very important role in principal component analysis in the process of reducing the dimensionality of a huge data set. Okay. Now, of course, there are several methods in QR decomposition, but most programming friendly method and most valid and applied method is Gram-Schmidt method. We are going to discuss how to reduce a matrix into QR factors with the help of Gram-Schmidt process. Okay. So here we can see A is a product of two matrices QR, where Q is nothing but a matrix with n vectors Q1, Q2, so on Qn, where Q1 is a column vector, Q2 is a column vector, and Qn is also a column. So each column is treated as a vector, then Q contains n column vectors, and R is an upper triangle matrix, which is shown here. This is R. This is R and this is Q. So this is Q and this is R. So what is the behavior of Q? That means how could you understand the Q matrix Q and how could we understand the matrix R? Here, when we decompose a matrix into product of two matrices Q and R, when we decompose a matrix A into product of two matrix Q and R, okay, then Q is nothing but an orthogonal matrix. That means Q is always an orthogonal matrix and R is an upper triangle matrix. What do we mean by an orthogonal matrix? Let us try to understand. Suppose if I write Q as like this, 1, 2 and minus 1, or let us for simplicity's sake, let us take a 2 by 2 matrix. Q is equal to 2, 1, and the first column as 2, 1, and second column as uh, minus 1 and 2. Okay. Now let us check what happens if we multiply q1 and q2 under dot product of vectors. Then we'll observe that 2 into minus 1 plus 1 into 2, that is equal to 0. That means the first column vector and the second column vector q1 and q2 are behaving orthogonal to each other. That means dot product is 0. That means both vectors are orthogonal to each other. So when we call a matrix Q as an orthogonal matrix if every pair of the columns behaves orthogonal to each other. That means whenever Q is called an orthogonal matrix where Q contains Q1, Q2, so on Qn, whenever Qi into Qj, the dot product of Qi and Qj is 0 for every pair I and j. That is called an orthogonal matrix. And of course, here we also see that every column vector is a unit vector. That means the norm of every Qi is equals to 1, and hence we can say that Q is an orthogonal and normalized orthogonal matrix. And what do we mean by an upper triangular matrix? Simple. An upper triangle matrix is nothing but the matrix in which all the entries lying below the diagonal. Suppose if you see this, all the entries below the diagonal are zeros. Then we can form a right triangle with the elements above the diagonal. That means if we are able to form a triangle with the elements above the diagonal where the diagonal below are 0 and above are non-zeros, then this matrix is called upper triangle matrix. That means if the elements lying below the diagonal are 0, it is called upper triangle in the perspective of non-zero elements which are lying above the diagonal. Okay, so we could understand what is an orthogonal matrix and what is an upper triangle matrix. So Q is called an orthogonal matrix if Q is imagined as Q1, Q2, Q3, 3 columns, and Q1 dot Q2 is 0, and Q2 dot Q3 is 0, and Q1 dot Q3 is 0. Then we say that Q is orthogonal. And R is called upper triangle matrix if all the elements lying below the diagonal are zeros. So this is what we understand from the meaning of orthogonality and upper triangularity of a matrix. Now, if you see a little deeper into the sense of orthogonality of a matrix, we can understand a few things. If a matrix Q is orthogonal, then automatically its transpose becomes its inverse. It is a property which automatically attained to the definition of orthogonality. So, due to the behavior of inside vectors, automatically the transpose of Q will be equal to the inverse of Q, which is a rare phenomenon in the maths. So, with that, we can automatically see that Q into Q transpose and Q transpose into Q is always equals to I. Because the transpose is its inverse itself, we can understand that Q into Q inverse, that is Q into Q transpose, is always equal to I. And also, we can observe that the det of an orthogonal matrix is equals to either plus 1 or minus 1. It cannot be other than 1 or minus 1, which could be easily proven that with this equation. Okay, so this is about a orthogonality matrix and an upper triangle matrix. That's what which we have discussed now or reflected in these lines. Vector q1, q2, qn are orthogonal and orthonormal if each vector is of unit size and the product of every pair of vectors is 0. That's what we have discussed now. And if all the elements which are lying below the diagonal are 0, that is represented with the line RIA is less than 0, we can switch the signs, and the vector RII greater than 0. That means we can summarize these things that the elements lying lying below the diagonal or zeros, then it is called upper triangle matrix. Okay. So, here we can reduce any matrix, any given matrix, whether it is square or rectangle, we can decompose it into product of two matrices. First matrix is called Q and the second matrix is called R factor, Q factor and R factor. Sorry. Q factor and R factor, where Q is orthogonal and R is upper triangle. So, if or the order of A is m by n, then we can decompose A into Q into R, where Q is m by n matrix and R is an n by n matrix. Okay. So let us see how the order is being split. If A is of order m by n, then Q follows the same order, but R will be in an n by n matrix. So, and Q is orthogonal, that means Q transpose into Q is equal to, just now I have discussed with you, and Q transpose into Q is equal to I. And R factor upper triangular with all non-zero diagonal elements and all elements below the diagonal are zeros. And all elements above the diagonal are non-zero. That is what upper triangular matrix. Now, here, for your better understanding, I am presenting an example. Here we have a matrix A, which is of order 3 by 4. Isn't it? Oh no, it is of order 4 by 3. Because it has 4 rows, 1, 2, 3, 4. 4 rows and 3 columns, 1, 2, 3. So it is a matrix of 4 by 3. Now, of course, we'll learn it in the next class. Now, I'm just giving it as an example. After decomposing it into product of two matrices, Q and R, you can check the product of these two matrices will be exactly equal to U. And the first matrix we obtained here is given like this, and second matrix is given like this. Let us verify whether the first matrix is orthogonal and orthonormal, and the second matrix is upper triangle. Let us take Q here. Q is minus 1 by 2, 1 by 2, minus 1 by 2, 1 by 2, 1 by 2, 1 by 2, of course, and 1 by 2, 1 by 2, minus 1 by 2, minus 1 by 2, 1 by 2, and 1 by 2. Now let us name these vectors as Q1, Q2, and Q3. Let us name these vectors as Q1, Q2. Now let us find the dot product of Q1 and Q3. Q1 dot Q2. That means minus 1 by 2 into 1 by 2 plus 1 by 2 into 1 by 2 plus minus 1 by 2 into 1 by 2 plus 1 by 2 into 1. What happens? It becomes minus 1 by 4 plus 1 by 4 cancelled and becomes 0. Minus 1 by 4 plus 1 by 4 cancelled and becomes 0. So the dot product is 0. In similar way, you can find Q1 dot Q3, which is equal to 1 by 4 minus 1 by 4 minus 1 by 4 plus 1 by 4, and automatically we'll get the answer 0. Now, if you multiply Q2 with Q3, it becomes minus 1 by 4 minus 1 by 4 plus 1 by 4 plus 1 by 4, and hence the result is. So, every pair, the dot product of every pair, that is Q1 dot Q2 is 0, Q2 dot Q3 is 0, Q1 dot Q3 is 0. That means every pair is behaving orthogonal to each other. And also, we can easily verify that. And also, we can easily verify that norm Q1 is equal to root of minus half square plus 1 by 2 whole square plus 1 by 2 whole square plus 1 by 2 whole square. Sorry, minus 1 by 2 whole square. This norm of a vector ABCD, the formula norm of a vector ABCD is nothing but norm of this vector ABCD is nothing but root of A square plus B square plus C square plus D square. The same formula we are applying here, and hence we get norm of Q1 as root of minus half square plus half square plus half square minus half square and plus half square. So ultimately we get 1 by 4 plus 1 by 4 plus 1 by 4 plus 1 by 4. That is root of 4 by 4. That is root 1 and hence 1. So in the same way, we could verify norm of Q2 as 1 and norm of Q3 is also 1. So what we have finally observed, we observed two things. Namely, finally, we have observed that Qi dot Qj is 0 for every pair I and j, and norm Q1 is 1 and norm Q2 is 1 and norm Q3 is 1. With this, we conclude that this matrix Q is an orthonormal matrix. Q is an orthonormal matrix. Okay, and hence the first condition has been satisfied. In the QR decomposition, the first matrix should be an orthonormal matrix that we have verified successfully. Now, let us come to the second matrix. R, where R is R11, R12, R13, R22, R23, R33, and here this is our R, and here we clearly observe that diagonal elements are non-zero and the above diagonal elements are also non-zero. Both diagonal elements as well as the elements which are lying above the diagonal are also zeros. That means we can form a right triangle with the help of all non-zero elements, and the non-zero elements are lying above the diagonal. That is why it is called upper triangular matrix. That means the elements which are lying below the diagonal are zeros and above the diagonal are none. That is the property of upper triangular matrix. And hence, we have successfully verified the second condition of QR decomposition. So, by mixing all these things together, we observe that A is decomposed into two matrices Q and R, Q into R, where Q is orthonormal matrix and R is an upper triangular matrix. And the question how we can reduce A into an orthonormal product of two matrices where Q orthonormal matrix and R is upper triangular matrix, the process will be explained in the next class. So, some applications, some practical application. One of the mathematical application of QR factorization is nothing but it helps us in finding pseudo inverse. What is pseudo inverse? It is an interesting. Generally, in our elementary matrix theory, we have come across the fact that a matrix A will have inverse if and only if it is non-singular. That means A inverse exists only if that A is non-zero. That is known to us. That means we understood that A don't have inverse if its det is 0 as well as A is a non-square matrix or rectangular matrix. That means we know these facts. A matrix will have inverse only if the det is non-zero and the matrix is a square matrix. If det is 0, the matrix does not possess the inverse, and if the matrix is a rectangular matrix, the matrix doesn't possess an inverse. So, in order to overcome this drawback, the mathematicians introduced the concept of pseudo-inverse. Pseudo-inverse is designed for those matrices who are failing to have an inverse. That means pseudo-inverse is designed for rectangular matrix, and pseudo-inverse is designed for non-singular matrices. Okay, so it will replace the role of inverse in the case of rectangular and singular matrices to maximum possible extent. That is the motivation behind pseudo-inverse. So pseudo-inverse has a definition, has a formula. Let us look into that formula and definition. So this is the definition of a pseudo-inverse. Pseudo-inverse is denoted by the symbol A plus, where it is defined as A transpose A whole inverse into A transpose. That means whether det A is 0 or non-zero, Delta A is 0 or non-zero. If the matrix is non-zero, definitely delta of A transpose into A will be non-zero. So with this idea, they have defined the pseudo inverse as A plus as A transpose A whole inverse into A transpose. Of course, it is motivated with this idea. Let us check. A inverse is equal to A transpose A whole inverse into A transpose. Then it becomes A inverse and A transpose whole inverse into A transpose. And it becomes A inverse. So with this motivation, they have defined with this motivation they have defined the pseudo inverse as A plus is equal to A transpose A whole inverse into A transpose. We don't know whether A transpose into A has inverse or not, but we have defined it like this. But we can approximate it with the help of QR decomposition. Now, any matrix, whether it is singular or non-singular or square or rectangular, it could be reduced into the form of Q into R, where Q is orthonormal and R is upper triangular. So let us substitute K is equal to QR here. Then what it becomes? QR whole transpose into QR whole transpose. That is what we have written. QR whole transpose into QR whole inverse into QR whole transpose. That is what we have written. Now, we know AB whole transpose. AB whole transpose is always equals to B transpose into A transpose. That is why QR whole transpose becomes R transpose Q transpose. Okay. And QR whole transpose becomes R transpose into Q transpose. And then we know Q is an orthonormal matrix. Q is an orthonormal matrix means Q is orthogonal means Q transpose into Q is equal to I. So this part becomes I, identity matrix. Okay, let us write it more clearly. This part becomes I, identity matrix. So R transpose into I into R, that means it becomes R transpose into R. So R transpose into R whole inverse into R transpose Q transpose. Now, you know this formula, AB whole inverse can be written as B inverse into A inverse. So, RT into R whole inverse can be written as R inverse into R power minus T. And R power minus T into R power T obviously becomes I, because RT whole inverse into R power RT is equals to I. So, this product becomes I, and hence we get R inverse into Q transpose. So we got a solid formula to find pseudo inverse. Now this becomes the definition of pseudo inverse. So pseudo inverse is defined as, now this becomes the definition of pseudo inverse, and hence pseudo inverse of a matrix, whether it is singular or non-singular, square or rectangular, we can define pseudo inverse as R inverse into Q transpose. R inverse into Q transpose. Q transpose, of course, automatically exists, because, and R inverse definitely exists because R is an upper triangle matrix where the diagonal elements are non-zero, and hence R inverse exists. Okay, that is why we can guarantee the existence of this product, and hence we can guarantee the existence of pseudo inverse. Okay, so from here onwards, the definition of pseudo inverse of any matrix is nothing but A plus, which is nothing but R inverse Q transpose. Okay, this is an application of QR decomposition. Of course, we have seen this example, and we will see the problem how to reduce a matrix into QR product of two matrices Q into R with the help of Gram-Schmidt matrix process in the next class. And now I'll close the class with a simple discussion of QR decomposition, association of QR decomposition with machine learning. QR decomposition, see these lines, QR decomposition can be useful in machine learning applications. An example of using QR decomposition in machine learning is the automatic removal of an object from an image. That means image processing. In the process of, in the lines of image processing, uh, QR decomposition plays an important role in dimensionality reduction. That means we can crop the image and we can remove some unwanted object or unnecessary object with the help of QR decomposition. Uh, that means because every image is nothing but a matrix which is expressed in the form of pixels, like 100 by 100, 100 by 100 pixels, 200 by 400 pixels. So every image can be understood as a matrix in terms of columns and rows as pixels. So with the help of QR decomposition, we can remove an object, unwanted object from the image. Let us see a small example and we'll close the class. Here we have an image of a car where it has a background where it is standing on a floor, and it has an emblem behind the screen. Now we want to remove that name car, and also we want to change the background into another color. So that comes an image person. To remove this name and to change the background, we have applied automation processing, which is auto editing through machine learning algorithms, which takes the help of QR decomposition, and the image is processed into a particular required color, green color background, and the floor has been removed and the name has been removed, the objects, and only less area of floor is being depicted. Of course, we can do it through manual editing, which is a complex file process. It takes a lot of time and a lot of stress, but through machine learning algorithms, we can easily process the image. And within that algorithm, these decomposition, matrix decompositions plays a very vital role, which is known as dimensionality reduction. And you can see um, here two vectors. Say this is the matrix A, where the first vector is 3 and 4, the second vector is 7 and 5. Now, if you draw the vectors 3 and 4, that is, this is 3, this is 4. When you plot this vector on an XY plane, you will see the red colored line like this. And if you plot the second column 7, 5 on an XY plane, you will see this blue line. So both vectors are established or projected on an XY plane like this, plotted on an XY plane like this. Now, when we have decomposed A into Q, A is equal to QR, the matrix Q contains two vectors Q1, Q2, which are given by Q1 and Q2 here. If you see, Q1 is represented with yellow and Q2 is represented with blue. And if you can clearly observe that the size of this vector is exactly unit length, and the size of this yellow vector is also exactly unit length. So both are unit vectors. And if you see, the angle between these two vectors is 90 degrees, and hence both are orthogonal. So both are orthonormal vectors, and hence Q is an orthonormal matrix. Okay. And similarly, when we go to the next slide, here you see the matrix R is represented with the yellow line R1 and blue line R2. Because the elements lying below the diagonal are 0, automatically the first vector will be a vector along y-axis, and the second vector can be any vector. Okay, so you can observe that definitely at least one vector will be along y-axis. That is the upper triangularity of the matrix. So this way we can understand the geometric understanding of QR decomposition. With this, I'd like to close the class, and in the next class, we'll continue our discussion on QR decomposition. We'll see the mathematical procedure of reducing the given matrix into product of two matrices Q and R. Thank you for your patience. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.